Hi everyone, this is Bharat. In this video, I'm going to present about the topic deep learning of subsurface flow by using theory-guided neural networks. So before talking about theory-guided neural network, let me give some brief introduction about a deep neural network and its limitations that led to the development of theory-guided neural networks. So this figure shows the typical architecture of a deep neural network, which consists of input layer, hidden layers, and an output layer. Each hidden layer has a specific number of artificial neurons, which are represented by circles. Each neuron receives an input and generates an output by using an activation function. The input layer provides the input for the first hidden layer, and the first hidden layer utilizes it to generate an output which becomes an input for the second hidden layer. And this process repeats over and over until the final hidden layer that produces the output vector. This output vector represents the prediction result of neural network. This figure shows how the input vector is received by neuron and how it utilizes that to produce an output by using the activation function. So in this figure you can see the input vector actually it's comprises of elements x1, x2 and so on up to xn. And these elements are modified by using network parameters such as weights and bias of the hidden layer. And the modified input vector is fed into the activation function, and the activation function finally it generates an output. This slide shows the forward formulation of a deep neural network. The first equation represents the output of the first hidden layer, followed by the output of the second hidden layer, and as I mentioned earlier, this process repeats until the final hidden layer produces the output vector y, which represents the prediction result of neural network. After generating the output, the loss function is generated by combining the predicted result of the neural network and the actual ground truth. This loss function indicates a mean square error between the neural network output and the ground truth data for different sample points that are used to train the neural network. And during the optimization process, this loss function is minimized and the network parameters are adjusted to obtain the parameters that produce accurate estimates. Once the optimum network parameters are obtained, then the DNN is set to be trained and it can be used to obtain the predictions for the new inputs. However, there are certain limitations of deep neural networks. In order to produce accurate estimates, deep neural networks need large amounts of data, which is really difficult to acquire in engineering practices, and it's also very time consuming. On the other hand, DNN may also produce physically unreasonable results, as it doesn't incorporate scientific knowledge and it's purely a data-driven approach. This figure shows the architecture of a theory-guided neural network. It's very much similar to that of a deep neural network, but the difference comes from the fact that it incorporates the scientific knowledge in addition to the data. So here you can see this orange box shows that in addition to data, the theory-guided neural networks also considers partial differential equations, boundary conditions, initial conditions, expert knowledge, and engineering controls to restrict the model to produce physically reasonable results and accurate estimates. Now let's see how to construct a theory-guided neural network. In case of learning the subsurface flow, the first equation here actually represents the governing equation of the subsurface flow in a homogeneous porous medium, whereas G denotes the specific stories, K denotes the hydraulic conductivity, and H denotes the hydraulic head. And the boundary conditions and initial conditions for the subsurface flow are given by the last two equations. This slide is about the residual and penalty functions. In order to enforce the governing equation, it is essential that the residual, which is the difference between the left hand side and right hand side of the governing equation, should be equal to 0. Similarly, the residual of the boundary conditions are also obtained by taking the difference between the left hand and right hand side of the boundary conditions, which are also required to be 0 in order to constrain the model to the boundary conditions as well as initial conditions. As theory-guided neural network, it also takes into account the engineering controls and expert knowledge. So whenever the neural network model violates the engineering controls and expert knowledge, a penalty function is imposed, and these penalty functions they are obtained by using some activation functions which takes input as these engineering controls and expert knowledge. After obtaining the residual and penalty functions, the mean square error is computed for each of those functions from the sample points that are used to train the theory-guided neural network. And this equation represents the mean square error of residual as well as penalty functions that I mentioned earlier. And finally, combining all the mean square errors, loss function is generated. And the coefficients of the mean square error here actually represents the weights of the mean square errors, and these weights are initially considered same, and as the optimization progress, they are adjusted to produce the accurate estimates. During the optimization, the loss function is minimized by using some optimization algorithms. And finally, these are some results as well as the reference models. Which are shown to compare the performance of theory-guided neural networks with that of deep neural networks for a specific hydraulic conductivity field. And these figures in the top row, they represent the reference theory-guided neural network and the deep neural network related hydraulic head over a region at a specific time step, that is at the time step 50. And the curves in the bottom row actually represents the variation of hydraulic head with x at a specific y coordinate. The left hand side represents the results of a theory-guided neural network model, and the right hand side represents the results of a deep neural network model. So from these curves you can see that the deviation of the predicted result from the reference is almost negligible in case of a theory-guided neural network, but in case of deep neural network, the predicted result actually is deviated a lot from that of the theory-guided neural network. From the reference curves. So from this we can conclude that the predictions made with theory-guided neural network, which incorporates the scientific knowledge, engineering controls, and expert knowledge, produce much more accurate estimates as well as physically reasonable results compared to that of deep neural networks, which is purely a data-driven approach. So the following are the references that I used to make my presentation. Thank you for watching this video.